I was hoping we could I was hoping that we could do physics because math, my syllabus is done for the term,
Okay.
and physics, I'm supposed to be starting with stoichiometry today again.
Okay, I just want to make sure you're writing a physics test soon. Do you know that?
Yes, yes, sir, on the 8th of September.
Okay. Can you do all the work there?
On physics.
Yeah. Electrical
Yes, sir.
currents,
Yeah, I've
electrostatics, and what else? What else is one thing? It's just those two things.
and electromagnetism.
Yes. But we haven't done any
Yes.
Faraday stuff. Are you happy with that?
We did do actually a
Oh,
couple. So when you showed me that,
yeah.
and you said calculations are not gonna be there as much. It's just the theory I have to focus on.
Yeah. But you've worked through examples in your textbook.
Yes, sir.
Okay, you're lucky we can do that because we have no one else in the class. If there were other students in the class, we can't just jump between physics and science, eh?
Yes,
Sorry,
sir.
maths and science. Okay, why not? Okay.
Yes, sir.
Stoichiometry.
Yes, sir.
So we haven't done any of that.
We did do it term 2, sir.
Oh, there we go. This is what we've done. Let me just have a quick look. All right, so you've got that. Okay, so we've done, okay, what we basically did in term 2 is just the basics. We did a percentage composition. We did, what else did we spoke about limiting reagents. No, we didn't. We did Avogadro's constant. We did this.
Yes, sir.
Okay, we did a little bit of concentration work. Where's this other stuff I'm looking for? Okay, I don't know. I can't remember. Okay, but the stoichiometry you're talking about now is what? Is it acids and bases?
I feel like it's the same thing, sir, because on my guided learning, it didn't tell me exactly. It just told me like the topic, which is stoichiometry.
All right. Can you still do this? Do you have
Yes,
this
sir.
little flow diagram I've got here?
Yes, sir. I was doing it yesterday, sir.
All right. Now, what I'm going to do now, we are going to do stoichiometry, but we are going to do a subset with acids and bases.
Okay, sir.
So I just need to make a subset here. I can't remember. Or maybe I should just do a new section group. Because I'm pretty sure that that your test is going to include acids and bases.
Yes, sir.
Okay, I'm pasting this thing again because we can use this, always use this. Okay, I'm just going to start off by just playing around with normal stoichiometry, but using specific ingredients, specific reactants that are acids and bases. Look, the way to treat it is exactly the same, but I'm just going to get you used to acids and bases. So your acids and bases, you have a whole chapter on acids and bases. And there's a lot of theory there.
Yes, sir.
We're not going to cover that now. And then they have a section on titrations. Titrations. We're going to be looking at that section because that section is stoichiometry. And this includes normal stoich and normal stoichiometry, and it also includes concentration work. So this is like, there's a lot included in there. So let's say, for instance, I'm just going to do a normal equation and then explain what a titration is. So say, for instance, I have sodium hydroxide in a solution. And we have 120 milliliters of the sodium hydroxide Can you remember that a cubic centimeter is the same as a milliliter?
Oh,
And
yes, sir.
cubic decimeter is the same as a liter. And this is normally your standard, this is your standard unit, liter or cubic decimeters. So I've got sodium hydroxide, and I don't know the concentration, but I just have a bottle of 120 milliliters of sodium hydroxide. And then I add, let's say hydrogen chloride to that, 85 milliliters. And the concentration is known, it's 0.2. Now square brackets just means 0.2 mole per cubic decimeters. So that's shorthand for concentration. Okay. And then we have sodium chloride. Okay, this is also in a solution. So then after those two react, this is a acid and a base. The hydrogen chloride is an acid and the sodium hydroxide is a base. They react with one another and they form a salt, sodium chloride in solution and water. So when acids and bases react, they give you get a salt and water, or a salt, water, and carbon dioxide, depends on what base we use.
Yes, sir.
Okay, now the word titrate basically means that we've done a specific type of experiment so that both of these two are actually have neutralized one another. So titrate means we have added these two together in such a ratio or such quantities that they both have neutralized one another. It means there's none of that is in excess anymore. So I just want to know, what is the concentration of sodium hydroxide? Right. So I'm going to show you a little picture of basically what we're doing. We've actually taken like a flask. It's called an Alamara flask or a conical flask. And we've added the sodium hydroxide in that flask. That was 120 ml.
Yes, sir. Can I ask, sir?
Yeah. Yes, obviously.
Isn't concentration equal to moles divided by the volume?
Yes.
So we can use that formula to calculate, right?
Yes. The problem is we don't have the concentration. We don't have the moles now. Is that true?
Yeah.
But
okay,
you can
sir,
get it.
Yes, sir.
Okay, good. Right. So what we've done here, we've taken that base, and that was 120 milliliters. And now we added an acid. The acid we added was 85 milliliters. And the concentration was 0.2. Now what happens, what you basically do, you put an indicator in. Do you know what an indicator is?
Yes, sir.
It changes color the moment the solution is neutral. So the minute you've added, or let's say the second you add enough acid to neutralize the base, then the color changes, and then you stop the reaction.
Yes, sir.
So there's no, in this reaction, there's no limiting reagent. Okay, so you're correct. This is method one. So I'm going to show you two methods of doing it. Method one is exactly what you want to do. You want to go to the HCl and work out the amount of moles. Is that correct?
But sir, okay, didn't you say you must calculate the thing, I mean, the moles of
sodium hydroxide.
Sodium hydroxide.
Yeah,
yes,
but how do you calculate the amount of moles of sodium hydroxide?
Oh, sorry, I just used I wanted to use the other
The moles
formula.
is the concentration times the volume, but I only have the volume, I don't have the concentration. But there's another way, look, a stoichiometric way to do it. And this is where this little block comes in. You start with a 1. Okay, we start with the concentration of the 1. Then we work to that mole. And then we have a ratio. And okay, this doesn't have to be products. You don't have to work from reactants to products. You can work from reactants to reactants. So look at this equation. If I can only find the amount of moles of HCl, then I know it's exactly the same as the moles of sodium hydroxide because they are in a 1:1 ratio.
Yes, sir.
So I can't determine the amount of moles of sodium hydroxide, but I can determine the amount of moles of the hydrogen chloride.
So can I be asked, right?
Pardon?
May I please ask, I used liters all the time, or do I still continue using milliliters?
No, you must use liter.
Okay, so divided
So the
by
concentration
1,000.
is 0.2 and the volume is 85 divided by 1,000. That's correct.
Which is 0,085.
Yeah, but I let the calculator do that. Otherwise, I make a small mistake in my head, and then I'm going to be really upset. So that's going to 0.017 mole.
Yes, G per mole.
Okay. No, it's just mole.
Oh, just mole.
Therefore, the sodium hydroxide, the mole is also 0.017. Because there's a 1-to-1 ratio in the reaction.
Oh, okay. So, sir, when you're doing titrations, the ratio of the thing is always equal.
No, not necessarily. It's just in this case, it's equal. Look, there's one sodium hydroxide for each one hydrogen chloride. I'll show you another one now that's not 1-to-1. See that? This is
Yes,
a
sir.
balanced equation. So the ratio in which they react is 1-to-1. So there's 1 mole of sodium hydroxide for each mole of hydrogen chloride. So now I've got the mole of hydrogen chloride, so I've got the mole of sodium hydroxide. So now I can
Also,
yes.
we just use the hydrogens, the hydrogen atoms, right?
No, you didn't. You looked at the invisible number 1 in front of both of them.
Oh, okay.
So your stoichiometry is a bit rusty.
Yes, sir.
Look, they react in a 1-to-1 ratio. There's invisible 1 in front of that because that's balanced already.
Yes,
So
sir.
whatever mole of the one I have exactly the same mole of the other one in the reaction.
Yes, sir.
Okay, I'll do another example after this. And then I can do this equation. The mole is the concentration times the volume. So the concentration is the amount of moles divided by the volume. And that is 0.017 over the volume of the sodium hydroxide, which is 120 mole, which I need to convert to liter.
Which is 0,12.
Yeah. And therefore, for concentration of 0.14 mole per cubic decimeter. That's the concentration of the hydrogen chloride. Okay, now, don't write this down yet. I'm going to show you another method, which is called the titration formula. I don't really like this method, but for a simple titration like this, it works really well. And you have a formula called Na over Nb equals Cv on top of Cv. Right,
Yes,
now, those Na, Nb means the ratio in which the acid, small a is for acid, and small b is base. So the ratio in which they react is 1-to-1. So it's 1 on top of 1. Where did I get those ratios? Well, the invisible ones in front of each one of those.
Yes, sir.
Okay, now the concentration of the acid is 0.2 times the volume of the acid. I'm allowed to use 85 milliliters here if I want to.
Okay.
As long as I use milliliters at the bottom, because then those milliliters will cancel.
Yes.
So it doesn't matter
Okay.
which unit I use as the volume. I could have converted to liters, both top and bottom, but then dividing with 1,000 will just cancel one another.
Yes, sir.
And then I put the C in here because the C of the base is outstanding. The concentration of the base is outstanding. And then I multiply across. So I have 120 concentration of the base equals 1 times 0.2 times 85. So I multiply across. And then I get concentration of the base as 0.14 mole per cubic decimeters. Same answer. Okay, so this blue method works really well in a simple titration. But if the sum gets really complicated, which it will, then the red method is the more secure one and the one that can actually pull you through. So I'll do another one. At the moment, you don't need to focus on titration. You only need to focus on stoichiometry.
Okay, so can I ask you a question, sir?
Yeah.
Okay. Since sodium hydroxide and hydrochloride, right?
Yes.
when they have two atoms that are the same, you use the ratio according to the two. Or
No, you look at the invisible one in front of it. Look at this piece of maths. I have 3x squared plus x squared. What value is right in front of the x squared that you can't see?
1.
1. It's the same if I have sodium hydroxide and there's no value in front of it, there's an invisible 1 in front of it.
Okay, so if it is 3 sodium hydroxide and plus hydrochloride, what would I do?
Then we would have said the ratio is 1 to 3. Let's do an example like that. Okay.
Okay, so
Now I'm going to take another acid and base reaction. I'm going to take sulfuric acid and potassium hydroxide, and that's going to react to give me potassium sulfate plus water. Now I have to balance this equation. Okay, that's AQ, L, AQ. So now the balanced reaction looks like that. This is a balanced equation. So now the ratio of sodium hydroxide, of sulfuric acid to potassium hydroxide is 1 to 2. Can you see that?
sir, oh, please repeat.
Can you see that the ratio is now 1 to 2?
Okay, yes, sir.
So there's 1 in front of the acid, that invisible 1.
Yes, sir.
Okay, now I have 100 milliliters of this base with a concentration of 0.15, and I have 60 milliliters of the acid, and I don't know the concentration. So the question is, what is the concentration of the sulfuric acid? Okay. I'm going to do method 1 again first. Method 1 is working out the mole potassium hydroxide. The mole is the concentration times the volume. That's 0.15 times the volume of 0.1, or 100 times divided by 1,000. That will give me 0.015 mole. Huh.
Yes, sir.
Right, now look at this. I can now get the mole value of the acid, H2SO4. The mole is in a 2 to 1 ratio. For every 2 moles of potassium hydroxide, I only have 1 mole of acid. So I can take the KOH, which is 0.015, and divide it by 2, because there's a 2 to 1 ratio. So if I have if I have 2 moles of potassium hydroxide, I get 1 mole of it reacts with 1 mole of acid. If I have 4 moles, it reacts with 2. So it's basically half. So there's a 2 to 1 ratio. That will give me 0.0075. Huh.
Yes, sir.
Good. And now I can work out the concentration. The concentration is the moles divided by the volume. It's 0.0057. And the volume of the 60 mole, so it's 60 divided by 1,000. That I just pop into my calculator.
Okay.
0.125 mole per cubic decimeter.
Okay, so sir, at the beginning of the thing, we must make sure that we balance the equation, sir.
Yeah. Look, 99% of the time, they'll give you a balanced equation. They'll give you one that is balanced already.
Yes, sir.
Okay. Good. Let's look at method 2.
Yes, sir.
And this you can only do titrations. Na over Nb equals Cv on top of Cv. Now the ratio of acid on top is 1 to base is 2. The acid is the sulfuric acid, H2SO4, and the base is the KOH. Now, what values do we have?
Okay, you said the top one is the base, right?
No, the top one is the acid.
Okay, acid then. Okay, yes, sir, yes, sir.
And the bottom one is base.
Okay. Um,
I don't have
C3.
the concentration of the acid,
Yes, sir.
but I have the volume, which is 60.
Okay.
I have the concentration of the base, 0.15. I have the volume, 100. So now multiply across. 2 times the concentration of the acid times 60 equals 1 times 0.15 times 100. So this is 120 Ca equals what? 15. No.
Yes, sir.
So concentration of the acid is 15 divided by 120. Obviously 0.125 mole per cubic decimeters. The stoichiometry is going to become difficult. You haven't done
Yes,
any
sir.
percent. Have you done percentage purity and percentage yield? No.
No, sir.
Okay. All right. So what we've done here, we've worked with a specific stoichiometry type of stoichiometry that's called a titration.
Yes, sir.
And what you've realized, we've never asked how many of each of those products form. Huh.
Yes, sir.
Because it's got to do with two reactants that basically neutralize one another.
Yes, sir.
Okay, so now let's go back to normal stoichiometry. Yeah, so in this one, you also have to be able to work out concentrations. Stoichiometry. Okay. We've done limiting. We haven't done limiting reactants. No. No. Okay, we'll have to do that. Let's
Yes, sir.
do. We haven't done any limiting reactants. Nope. Right. Now you must look. You must be very vigilant now. Okay. So let's assume. I'm just going to show you the following. Let's assume I have magnesium, which is a solid, and I have
Yes,
like
sir.
15. Let's say I have 15 grams. It's actually a lot. And that is going to react in oxygen gas. And that will give me magnesium oxide, which is a nice reaction. If you haven't
Yes,
seen
sir.
this before, magnesium oxide is a nice white big flame.
Yes, sir.
Okay. They use it for lighting at night.
Yes,
Bomb.
sir.
Show. Yeah, there's a way to do. If you're in the army or something, I'll show you now what we'll after the sum. I'll explain to you what they do. Okay, let's say there is excess of the oxygen.
Okay.
This is an easy sum. So I want to know. Okay, good. One, how many mole? Okay, let's just balance that equation. How many mole of magnesium do we have? Okay, that's really simple. The amount of mole is the mass divided by the molar mass.
Yes, sir.
The mass is 15 and magnesium is 24. So there's a lot of mole there.
Yes.
15 divided by 24.
So, can I be asked, don't you always use, you use grams instead of kgs? I'm sorry. Yes, sir.
Yeah, we use gram. So this is a violent reaction. When magnesium, whenever one of your group 1 or group 2 metals react with oxygen, it's a violent reaction with a big flame that sends out bright light.
Yes, sir.
So I'll explain to you now what they use it for. One of them. Okay, so we have zero. Look at me, gram. It's not gram, it's mole.
Yes, sir.
0.625 mole. Good.
Yes, sir.
Right. Now the next question is going to be number 2. How many gram of magnesium oxide do we produce? So how many grams of magnesium oxide would we have? Okay, look at the mole ratio. The mole ratio is 1 to 2. Can you see that?
Yes. Yes, sir.
So I can go to the magnesium oxide and immediately say the amount of mole is 0.625 times 2.
Yes, sir.
For every 1 mole of magnesium, I'll get 2 mole of magnesium oxide. And there's a problem here with balancing. This wasn't balanced. Looks good. Sorry, there's a 2 missing in front of the magnesium.
Yes, sir.
So that's a
So
mistake.
that means,
Look, I haven't balanced the equation properly. It's only balanced now.
the thing stays the same.
It's
The
the same.
ratio is 2 to 2. Yes,
Yeah.
sir.
So that's the same. Bang. You see that?
Yes, sir.
So I've got the amount of mole of magnesium oxide. And then I can do the mole is the mass over the molar mass. So the mass is 0.625 times the molar mass. Magnesium is 24 plus an oxygen, which makes it 40. So I'm just going to multiply that with 40, and that gives me 25 grams of magnesium oxide. Okay, but this is really simple, isn't it?
Not really.
No, this is really simple. You need to write this down and say, this is example 1, and this is a basic stoichiometry. We have excess of something.
Yes, sir.
Okay, and then I'm going to wipe it to make it harder and show you what a limiting reagent is.
Yes, sir.
You can tell me when you're ready.
2. Yes, I'm ready.
Okay, now we're going to change this sign. I still have 15 grams of magnesium, for instance.
Okay.
But now I have, let's say 30, let's say 38 cubic decimeters of oxygen gas at STP.
Yes, yes.
Okay, so now I don't know. They haven't told me which one is in excess. So what's going to happen? The magnesium is going to burn. We're going to make a little experiment. I've got a glass tube there, and on top it's sealed, and on the bottom it's also sealed. And then I have a little burner there inside with a flame.
Yes, sir.
Flame. And then I've got a piece of aluminium. Not aluminium. Let's make the magnesium green. I've got a piece of magnesium that's green there, which we're going to burn. And obviously there's oxygen gas in here. So
yes,
this reaction will stop in either one or two, with other two ways. There's 2 things that can stop this reaction. One, the oxygen is finished and then the flame stops burning. And then the experiment stops. Do you agree?
Yes, sir.
Or the piece of magnesium that I've got there burns out and is finished.
Yes, sir.
And then experiments also stopped. If the piece of magnesium is burnt out, there might still be oxygen left in the container. No, you agree? But the experiment won't go on because there's no magnesium to burn. Or if the oxygen is finished, there might be a little piece of magnesium left, but there's no magnesium oxide forming anymore because the experiment's finished. The flame is not burning anymore. So you need to find out which one of those 2 will be finished first.
Okay.
So I
Yes,
need to
sir.
go and work out the mole of each one of them separately. So with the magnesium, the amount of mole is the mass over the molar mass. And that's 15 grams. And the molar mass is 24. And we got something like 0.625 or something.
Yes, sir. It's 0.625.
Okay, that's 0.625 mole. Then I can't do a 2-to-1 ratio because there's only a certain amount of oxygen gas.
Yes, sir.
I don't know, but I can work out physically how much mole there is by using this formula. The mole is the volume divided by Vm, and you've seen that.
Yes, sir.
Okay, so the mole is, the volume is 38, and at the STP, there is what? 22.4 cubic decimeters.
Yes. 22.
The mole is much more. So
Yes, sir.
38 divided by 22.4. And that gives me 1,6964 mole. Right. Now, it looks like the oxygen we've got lots more oxygen than magnesium, eh?
Yes, sir.
But you still have to find out exactly how much. Or there's a 1:2 ratio, so we're not even 100% sure. So I'll show you a method now. You take the magnesium and the oxygen, and you write the ratio. It's a 2:1 ratio. Do you agree?
Yes, sir.
And then you fill in one of those values. Choose anyone. Let's choose the magnesium. You fill in
Yes,
a
sir.
0,625 value, the mole value of the magnesium, and you make the other one X. You see what I've done?
Yes, sir.
Because we want to work out exactly how much of the oxygen we need to finish off the 0,625 mole of magnesium. And then you multiply across. So you get 2x equals 0,625. And then you divide with 2. So x equals what? 0,625 divided by 2. And that gives me 0,3125 mole. And this is the amount of oxygen needed. Amount in mole. So amount is not the right word. Let's just use mole. Mole oxygen needed. Okay. Right. So we only need 0,3125 mole of oxygen. Do we have more or less than that?
We have more.
We have lots more. You see?
Yes, sir.
That means the magnesium is the limiting reagent. And that means we must use the magnesium to determine the amount of magnesium oxide. Because it's the limiting reagent. In other words, what will happen? In this experiment, that green lint of magnesium will burn out first long before all the oxygen is used in the container. So that means we can't use the amount of mole oxygen to determine how much magnesium oxide forms. There's way too much oxygen to use that. We must always use the one that burns out or finishes the reaction first to determine how much of the product will form. Do you agree?
Yes, sir.
Right, so dot that down. Make notes.
Yes, sir. I did write it down.
Okay, so I'll show you what they do. So let's say, this is just for fun. Let's say we are in a big battlefield. And this is Army A. This is the men in Army A. And there's the enemy, Army B. So now we having like a fight, or we're shooting one another, but it's at night. So no one can see anything.
Yes, sir.
Then you take a magnesium bomb. It's a pipe. You put in it looks like a rocket, basically. It looks like this.
Yes, sir.
Okay. And you throw it in the pipe and you shoot it. And you see there's a timer on its nose. You set it for like 10 or 12 seconds. So it shoots out of the pipe right on top of the enemy's heads. But it's like, let's say, it's like 600 meters above sea level. It explodes.
Yes,
and it's got a little parachute on it. So it explodes, and then it starts burning on top of the enemy. So you can see the whole, you light them up. You can see where they are. And then they are lightened up, but you're in the dark. So they can't see you, but you can see them, and then you can shoot them.
Oh, that's smart. Yes, sir.
That's very smart. So you boof, the bomb goes off in the mid-air, and it's above their heads, not above yours. So you can see from the dark place where you are, you can see into the light area where they are. So you can see them clearly and shoot them, but they can't see you. So those are magnesium bombs. Defense forces used when they still existed, used. Right, let's do another one.
Okay, sir.
So now I'm going to take, let's say for instance, we've got potassium hydroxide.
Okay, sir.
Potassium hydroxide. This is like a base in solution.
Okay.
And we have a volume of, let's say, 60 milliliters. and we have a concentration of 0.2 mole per cubic decimeters.
Yes, sir.
I'm just going to do this. And now we're going to add acetic acid,
Okay.
CH3COOH. And this is a weak acid. And we have a volume of, let's say, 100 milliliters. And our concentration is lower. It's 0.17 mole per cubic decimeters. And that gives us CH3COOK plus water.
Okay.
What's that CH3COOK? It's potassium acetate.
Okay.
I think so.
Yeah.
Right, but I'm not worried about those two products. I want to know, one, how many mole of potassium hydroxide do we have? Okay, you write that down, and first you're going to work that out for me.
Potassium hydroxide, right?
Yeah, potassium hydroxide, KOH. How much do we
Yes,
have?
sir.
How many moles do we have?
Okay. N equals to V divided by VM. Okay. Which equals to 60 milliliters divided by 22,4.
No. We're not working with gas.
Oh, sorry, sir.
KOH. The concentration equals, or the mole equals the concentration times the volume.
Oh, forgot about that formula, sir. Sorry. N equals CV, okay, which equals to 0.2 multiplied by 6. Okay, it gives us 12, sir. Oh, but
that.
do we have to divide by 1,000 when it comes to the
Yes,
volume?
of course. You must work in liter or in cubic centimeters, or cubic decimeters.
Yes.
Come, Tatu.
It gives you 0.012, sir.
0.012 mole. Okay, good. Now, difficult question, number 2. Which one? So the potassium hydroxide or the acetic acid? Which one is the limiting reagent? So that means you must first go and work out the amount of moles of the acid.
Yes, sir. Okay, let me go do that right now. OH 0.7 multiplied by it gives me 0.017.
Okay, let's do CH3COOH. The mole, oops. Let's get that eraser. The mole is the concentration times the volume. The concentration is 0.17. The mole is 100 divided by 1,000. So you're right, 0.017 mole. Okay, good.
Therefore, potassium hydroxide is the limiting reagent.
Awesome. Why? This was very simple because it's a 1-to-1 ratio, isn't it?
Yes,
true?
sir.
Yeah. So this is easy peasy.
Yes, sir.
Okay.
But, sir,
Yeah.
I still don't understand how you find the ratios between the two.
Okay, look at this. There's invisible one in front of KOH, and there's invisible one in front of CH3. And that means it's a 1-to-1 ratio. Okay.
Oh,
Sometimes when you balance the equation, you'll have a 2 there in front, and then the ratio will be 1-to-2.
Okay, sir.
So now, yeah, you're right. Therefore, KOH is the limiting reagent. No, reactant. Okay. That means if I ask now the next question, number 3, I want to know what is I'm going to ask you a lacquer question now. What is the concentration of the CH3COO minus ions? So what is the concentration of this CH3COOH? So the concentration is the mole divided by the volume. So you need to find out what is how much mole of that potassium acetate forms.
Okay, we find in the concentration.
Which means what? You have to use the limiting reagent to determine that. You can't use the acid because the acid is in excess. Is that true?
Yes, sir.
So okay. So can you tell me, without doing any calculation, how much mole of that potassium acetate film is available or forms?
How many moles?
How many moles of the potassium acetate forms? 0,012.
Okay.
Because there's a 1:1 ratio with the potassium hydroxide. You see that?
Yes,
that you must get. Okay, because there's a 1:1 ratio. So now out of this, the mole is 0,012. What volume do we have?
60 milliliters, sir.
No. We've taken 60 milliliters of potassium hydroxide, throw that into one flask, and then we also threw in 100 milliliters of the acid.
So we have 160.
So in that flask, we have 160 milliliters. So we're going to divide that with 160 divided by 1,000, isn't it?
Yes, sir.
And that gives us 0,075 mole per cubic decimeters. Okay, this is an important sum.
Yes. Oh, this is difficult.
No, it's not difficult. This is not, sorry, but to inform you, but the difficult stuff hasn't started.
Oh.
Okay, you are just not, you haven't done a lot of stoichiometry, that's why.
Yes, sir. So, okay, can you do one last one, sir?
Yeah. Try and make it harder. This one is too easy. I have, what? Let's say beryllium hydroxide. Beryllium hydroxide. I'm going to keep it 2. Plus silver chloride. I don't know what happened with this pen tonight. Silver chloride. They're all in solution. I'm not going to do the subscripts.
Yes, sir.
Okay. And that gives me beryllium chloride plus silver hydroxide. No, silver hydroxide is just AgOH. Okay, I have to balance that. 2 here, 2 there. Good. So let's say I have 8 grams of silver chloride. And I'm going to put that, let's say this is a solid. It's not going to be, just make it a solid. And this is a solution. So let me just try and figure out something here. 8. I need to just do something weird here.
Yes, sir.
0,05. I have a volume, let's say 100 milliliters. And I have a concentration. I don't know. What?
0.27.
That's quite high. Let's make it 0.17. I just want to figure, just want to make sure it's going to work. Or work well enough. No, that's not going to work at all. I have 30 milliliters. No, I don't have 30 milliliters. Just give me a break here. I don't want to make it too easy for you. I have 300 milliliters.
Yes, sir.
Yeah. Let's do that.
Yes, sir.
It's going to be too easy. Sorry, I'm changing it again. I have 120 milliliters. There we go. I have 120 milliliters of beryllium hydroxide with a concentration of 0.17 mole per cubic decimeters. And I'm adding 8 grams of silver chloride to it. I want to know, ultimately, what is the concentration of the beryllium chloride?
Okay.
Now, first need to quickly guide you. The first thing we need to do is, which one is the limiting reagent? That means I need to get the mole of beryllium hydroxide. I need to get the mole of beryllium hydroxide. I also need to get the mole of the silver chloride.
Yes, sir.
Okay. Right. Do both of those for me.
Okay, sir. CL.
You can talk with me, and then I'm writing
Yes,
it
sir.
down.
Okay, the mole equals to C multiplied by V equal to 0.17 on the first one.
Yeah.
Multiplied by 120 divided by 1,000.
Okay. I get something like 0.0204. Is that correct?
Yes, sir.
0.0204 mole. Okay, good. Then the silver chloride, the mole equal.
Okay, you gave us the thing, right?
Grams.
Oh, okay. Oh, so the ratio is gonna be 1 to 2. So
Well,
therefore,
you can't do that because there's a limiting reagent. Let's first work out. We can calculate the amount of mole of silver chloride, so we'd better do it. Look, if I didn't give you any value, and I said, look, they two react with one another, then you can, and they neutralize one another, then you can actually do it. But now I might have too much. I must work out the mole there. The mole is the mass over the molar mass, isn't it?
Oh, yes, sir.
I can work out the mole. If I can work out the mole of both reagents or reactants, then one of them might be in excess. So I have 8 grams divided by silver, which is like 107 or something, or 108. I don't know. Do you know what silver is?
Let me just check in my thing, my periodic table.
Mine is not, yours are rounded off. Mine's not rounded off.
Must I give you the rounded off then?
Yeah, no, I think it's 108 on yours.
Yes, it's 108, sir.
108 plus 35.5 for the chlorine. Let's work up that. So I get 0.055749 mole. Okay, but now I'll be very careful. Although the silver chloride looks like more, we first need to get there's a ratio. So I'll be clever to do the following. The beryllium hydroxide to the silver chloride is in a ratio 1 to 2. So which one do you think is in excess? It's a silver chloride, eh? Because even if I double the beryllium hydroxide, I'm not going to get 0.05. I'm going to get 0.04. Can you see that?
Yes, sir.
So I'm going to make the one that I think is the limiting reagent X. Oh, no, sorry, it's this one. Man. It doesn't matter. It doesn't matter. You can make any one X.
Yes,
And
sir.
then I'm going to fill in this value as 0,0204. And then I multiply with 2 or multiply across. Then I get 0,0408 mole. Okay. Now, very important. This is X. And this is the amount needed in the reaction. Or the amount that does react. Or that does react. Very important. Okay, so I need 0,04 mole of silver chlorine. Do I have that?
Yes, sir.
I have more. You see
Yes,
that?
sir.
So therefore, there's too much of the silver chlorine, and therefore the beryllium hydroxide is the limiting reagent. Is that true?
Yes, sir.
And that means I need to use the beryllium hydroxide to determine the amount of beryllium chloride that forms, or the concentration. So this is step 1. This was step 2. This is step 3. So step 3 is the following. There's a 1-to-1 ratio with the beryllium hydroxide and the beryllium chloride. So
Yes, sir.
the beryllium hydroxide, I can have the mole for free. The mole is the same as the beryllium hydroxide, which is 0,0204 mole. Because there's between those two, there's a 1-to-1 ratio. And now the concentration is the mole divided by the volume. That is 0,0204. And the volume of that is just 120 mole. Can you see I've added a solid, which it didn't change the volume of the flask. There's still only 120 milliliters in it, fluid. Are you with me?
Yes, sir. Yes, sir.
So that is, so that is 120 divided by 1,000. There you go there. 0.0204 divided by 120 divided by 1,000. That is 0,17 mole per cubic decimeters.
Oh,
Okay, look at
yes.
that. No.
Oh. Okay, so I won't lie, this is very confusing, but I'll get used
Well, what
to
you're
it.
gonna do? You're gonna re-look at this video then.
Yeah, and I'm gonna practice on more some.
Okay.
Yes, sir.
Very important work. Very important.
Yes.
I'll see you next
Yes,
week.
sir. Good.
No, I'll see you tomorrow apparently.
Yes, sir. Tomorrow, because yesterday you were not feeling that well.
So tomorrow we're doing more, okay, of these.
Yes, sir.
Okay.
Sir, are you able to send me like more examples like this?
I first
via
want
my
you to do
email?
the ones in your textbook.
Okay, sir.
Okay.
Bye, sir.
So start with the textbook so you can guide me more or less of where you are. Otherwise, I'm just going to send you stuff to do, and you might miss out on some of this, the other stuff the textbook wants you to focus on. Okay.
Okay, sir. Bye.
Well.
Bye, sir.
Bye-bye.